All right, so last time I started with a one-to-one function and then showed how to create the inverse of that, recalling basically writing it as y equals, swapping x and y, and then solving for y. And that's how we got the inverse function. And then I went on quickly to just show, well, if I evaluated the function at 5, it equaled 2. So that meant if I evaluated the inverse function at 2, it should equal 5. In other words, they're opposites of each other. The domain and the ranges flip. And I showed that. But I want to pick up from there and mention that that's not proof that I got this correct. I could have made an error. Maybe that's not actually the inverse function of this. The only way to be sure is you would have to test every number, and that's not possible. So we're going to look at a test in a minute, but what I wanted to do quickly to illustrate would be to show a couple other functions here. This is a linear function, y equals mx plus b. We know it's a function, we know it's one-to-one. That's the way linear functions are. As long as they're not horizontal or vertical, then they're out of it. And then suppose we were given the fact that the inverse function of this is 1/3 x plus 1. So somebody come along and they said, I have a function, here's the inverse function, and I'm even going to test it for you. I'm going to put in g of 4, and that's going to equal 2 times 4 is 8 plus 1 is 9. And then I'll put 9 in the inverse function, and I should get 4 out. And as it turns out, 9 divided by 3 is 3 plus 1 is 4, so it looks good. Unfortunately, just about anything else you try in this function is going to bomb out. Let's look at g of 1. That's going to equal 2 times 1, that's 2 plus 1 is 3. So if I do the inverse of 3, I should get 1. But that's going to equal 3 times 1/3 is 1 plus 1. That's only going to equal 2, so these don't match. So it turns out it's not an inverse. So what is the test? How do we know for sure if it is or isn't? Well, the test is back to the composite function that we learned earlier. Since these guys undo each other, if I put them together as a composite function, then when I simplify everything, I should get x. So let's see how that works with this one. Since we know they're not inverses, it shouldn't equal x. So again, remember what the composite function means. It means that this function here replaces x in this function. So let's start with f. Okay, we got cube root of x, and instead of x, I'm going to put this function in place of x. Okay, we're substituting this entire function in for x in the first one. So instead of x, I write x cubed minus 3. And then I have this plus 3. So there's the composite function. Now I simplify it. These 3's cancel, and the cube root of x cubed is just x. So it works for this one. And unless I made a mistake, I knew it was going to work anyways because I used the technique and created that inverse function. But it should fail here, so let's try that. So for G and G inverse, if I want to test those two to see if they're inverse, here's G of X. Again, I got 2 times, and then instead of X, I'm going to put in all of this for X. So again, the composite function, take your first function and wherever you have X, you replace it with the other function, okay? All right, if we simplify this, you can already see it's not going to equal X. I got 2/3 X plus 2 plus 1, that's plus 3. That does not equal X, so we know for sure that's not an inverse. Although we figured it out anyways because we found a point where it didn't work. But what you want to do to verify an inverse is to use the composite function of the function and the inverse. That's the test. Okay, so if you have a function and it's 1-to-1, then you can find an inverse. If it's not a function, you don't even try. If it's a function, then you have to figure out that it's 1-to-1. Back in chapter 2, they talked about functions and they talked about looking at the curve and drawing vertical lines. And we looked at that in the last section. As long as a vertical line doesn't cross more than once, then it is a function. If you have a situation like this, and you get to here, the vertical line crosses twice, that means that's not a function, so that means you can't try and find an inverse for that thing. But unless you're given the curve, you're going to have to start with an equation and try and figure out if it's even a function. So about the only thing you can do here is look at the equation, go to the toolbox set in 3.1, and then try and do a rough sketch of the equation, try and do a rough sketch of its graph, and then inspect it. And that's probably the best way for us right now to figure out if something is a function, just to even get started. But another thing you can do is solve for y and see if you have multiple cases. So for example, if you go back to page 190, turns out example 3 has this shape and they're testing it to see if it's a function. Turns out it's not. But they give the equation. And one way algebraically that you can use to help figure out if an equation is a function is to solve for y. So for example, if I solve this for y, I got to take the square root, but you always do plus or minus on an even root. So I wind up with that. Well, you can see that I can have an x value associated with 2 different y values. That's what's happening here. For example, let's say x equals 4. Square root of 4 is 2. So when x is 4, y can equal 2. Or when x is 4, y could equal minus 2. And if you recall, if you are given a set of points, the x coordinate can't repeat. So that's the idea of solving for y, to see if you get multiple, at least two values that could be associated with an x point. So I have two different y values, but for one x point, so that's the idea of failing the vertical line test. Okay, what about one to one? Okay, so we can figure out if something's a function or not just to get started. But once it's a function, how do you know if it's one-to-one or not? That's, again, a little bit more difficult. Similar to this, our technique that we have, and probably pretty much what the book mentions, is, again, when you have an equation, you're going to have to try and draw the graph. But this time, you're going to inspect the graph with the vertical line test. So let's go back to this guy. Somebody says I got this equation. How do I even know that that's one-to-one? If it's not one-to-one, then I'm not going to be able to properly get an inverse. Well, one method, and the book suggests, is, again, to try and sketch the graph. So, and again, one way to do that, go back to section 3.1. Take a look at the various graphs, and one of them, the base graph, is cube root graph, and the cube root looks like this. And then do your transforms. In this case, we only have one. We're going to the left 3 units. So our final graph would look like this. 1, 2, 3, it's going to go through here. Okay, and it's going to look like that. So that's a lot of work, but this is one way to do it. If you can get a graph, then you do the vertical line test, because for one-to-one, you're trying to figure out, do I have more than one point for my y value. So in this case, I had x value repeated. For one-to-one, I don't want to repeat a y value, so I don't. For every y value here, I only have one x value. So if you had a curve, again, like this, we showed this one before, parabola. Parabola, it is, okay, if you go this way, we should check that. It is a function, okay? The vertical line only hits once, but when you use the horizontal line test, you can see that I got a lot of y values here where I have 2 x values. So I would have the same y value with 2 different x values. So it might look like, okay, here when y equals 4, x can be 2. Or if x is minus 2 squared, if this was, say, x squared, would still equal 4. You're going to get a repeat on the y coordinates. So vertical line test, which we learned before, but again, to use that, you have to have a graph. Algebraically, it's a little more interesting. If I have an equation, I'm not sure about the graph, one thing you can try and do, you can take that equation or function that you think, and you can evaluate it for 2 different points. But the idea is this. If I evaluate a function for a point A and it's exactly equal to that same function evaluated at point B, then that means A has to equal B. That's it, nothing else. So how would that work here? You would just say cube root of A plus 3 equals cube root of b plus 3. And then simplify all this and see if you can get down to a equals b. Well, you can see it's pretty easy. Cube both sides. So both sides get raised to the third power. Cube them. So these cancel, right? And a plus 3 equals b plus 3. Subtract 3 from both sides. A equals b. So the idea here is the functions are equal for two different values. Those values have to be equal. So it's 1 to 1. You're not really introducing a new value here. It's the same value. Okay. Let's see if I have any others we could try. Well, y equals x squared, for example. That's a function, but as we just looked here, it's not 1 to 1 because it fails the horizontal line test. But let's try this. Let's suppose we didn't know what the graph looked like. So if I think of this as f of x equals x squared, and now I'm going to try this test. So f of a would be a squared. F of b would be b squared. So if I simplify this, is a equal b? Well, take the square root of both sides, right? But when you take the square root, remember you got the plus and minus root. So plus or minus a equals b. So no, b does not just equal a, it can equal a positive a or a negative a. So therefore it fails the test algebraically, so it is not 1 to 1. Okay, so that's it for now. You do need to, just in the book, you can pretty much assume these things because they're going to tell you, or they're going to want you to just do the problem. But in real life, you do need to know that you're working with the function, and then you need to know that it is a 1-to-1 function if you're going to want to do an inverse. Now, next, in the next part, we're going to look at, there are a few functions that aren't strictly 1-to-1, but let me give you an example here, and we're actually kind of looking at it. I can't technically do an inverse of this function. However, if for some reason you wanted to do an inverse somehow, number one, if it's not 1-to-1, there's no inverse. However, I could do an inverse on just this much of it. So what we'll look at next time is restricting the domain of a function to allow you to write an inverse of just that portion of it. So that's one thing we'll look at, and then the last thing will be, what does the graph of an inverse function look like compared to the original function? So that's coming up.